Welcome to Applied Bioinformatics. Today's lecture is about significance and sampling. As a subtitle you can see, famous quote, there are lies, there are damned lies, and there are statistics. Sampling data, dealing with data, handling it properly, judging it properly is very, very difficult. And at the heart of bioinformatics, actually at the heart of all research, is of course data. So in today's lecture, I will tell you how to judge an alignment. You'll get to know z-score and e-values, and I'll give you some general ideas and insights and motivations into why statistics is actually really fun and what the culprits and difficulties are and what frequent misunderstandings are. Significance. A key question after a sequence comparison is the result significant? If you remember the first lecture, I told you about the mammoth and the Indian and African elephant, and there were 10 and 14 mismatches, and the conclusion was that there is none. Based on these differences, we cannot really decide whether mammoth and African or mammoth and Asian elephant are more closely related. The key problem is that the absolute value of a score itself is elusive. We have to compare it, we have to judge it. So consider more general a statement like Petra is tall, or Peter is tall for his age, or John had a 1.7 in the bioinformatics exam, is all exactly the same as comparing two sequences and obtaining a score of 27. It's essentially meaningless, and only in comparison to a control population we can judge whether it is significant. Significance judges the score with respect to a control population. But where does the control population come from? We can generate a control population randomly. How to do this from a sequence? We could just take turns and position by position, randomly select an amino acid or a nucleotide. Each one has a 1 in 20 or 1 in 4 chance to be selected, and position by position we create our sequence. Then we use many of these sequences to define the control population. We run the score on those control population entries, and then we can compare what we get out on average and the distribution to the actual score that we were after. But how good is that? Are randomly generated sequences really reflective of what you find out in nature? Now, first of all, although there are many sequences, they still do not cover all of the space of theoretically conceivable sequences. And then we have heard already about certain patterns that exist within these sequences that would not be really satisfied if we just randomly generate those sequences as we now suggested. When we discussed the substitution matrices, we took into account that some of the residues are frequent and others are rare. Tryptophan was among the rare ones, alanine was among the frequent ones. So if we generate sequences and we give the same probability of choosing a tryptophan than an alanine, then this is clearly not reflecting what is out there in nature. So what would be a better approach? Well, a better approach would consider at least the existing data and make estimates based on that. And judge, for example, how frequent the tryptophan and the alanine was. But then we have, of course, another problem, that the existing data may be biased. But even in the worst cases where there is no existing data at all, we simply have nothing given, we still have our query sequence. And we can turn our query sequence into a random sequence by simply shuffling around the residues. This will create a sequence that has exactly the same composition in terms of frequency of all of the amino acids, only the positions have changed. So that means you can create controls even if no data is given, and in the worst case, you create the controls randomly from the query data that you have. But of course, you must take into account that this control population has a bias which is introduced by the way you created that control population. So you may say, okay, better option is take a given control population. So we have a database. There is known data that we can use. But then there's another sort of bias, namely, how was this data sampled? How was it selected? How was it chosen? There might be different reasons underlying which are not so obvious. So think, for example, of the protein data bank that contains the protein structures that we looked at already. Structures are very difficult to obtain, so there will be bias in the database towards structures that are easy to obtain. There will be bias towards proteins for which it was easy to obtain funding. So these will be typically proteins which have some relevance to humans. Maybe they are disease relevant, maybe they can improve some processes if one has a deeper understanding about them. But ultimately, it's researchers behind this data. These researchers create the data. These researchers need money to create this data. They obtain it from somewhere, and they must justify why they generated exactly that data. And that introduced bias. We do not have an unbiased selection of everything that is out there in nature, but it's our human-centric view onto what might be useful and what not. So let's look at some really basics. You must have all learned about these things already in school, but I'll give you some questions which come from real life, and you can look at them and you can see whether you spot the problems. So what I want to talk about here again is the average or the mean value, median, variance, and standard deviation. And the average is defined as the sum of the values you have divided by the number of values that you have. The median, in contrast, is the middle value. You take all of your values, you sort them, and the one in the middle is the median. Now let's look at this difference between average and median, because they frequently get mixed up in language. So imagine, for example, there's a presidential election and you have two candidates. Candidate 1 is saying the average family pays more taxes. Candidate 2 is saying each family pays on average less taxes. Which is which? Or, first of all, are these two statements contradictory? Now, upon first glance, they do appear contradictory, but if you look closer, they're not. Both statements are valid. But the problem is that one is talking about the median and the other one is talking about the average. And it gets even more complicated because in natural language, we often use the word average when we're referring to the median. So candidate 1 is pointing to the average family, and the average family is the median. You have taken all families, you have sorted them by the amount of taxes that they pay, and then you picked up the middle one, and that middle one you checked whether it was paying more or less taxes. So candidate 2 was saying each family pays on average less taxes. So here, this candidate simply took all of the taxes that were being paid more or less and divided that by the number of families. Now, median and average do not make a difference if the distribution behind it is, for example, a normal distribution. They both, in a normal distribution, both average and median are the same. But things like taxes, salaries, and also in our biological setting, we frequently have this. Very frequently, we observe distributions that are not normal distributions. So simply by taking, for example, the logarithm, you get a log normal distribution. Quite frequently, you also see a so-called power law. The power law means that there are a few that have a lot and many that have a little. And it's kind of an exponential fit to a curve. Now, how would that be with salaries and income distribution in families? Well, that's of course the same. There are few who have a lot and there are many who have a little. And then the average and the median do not coincide on these distributions. So you must ask yourself, first of all, my data, what kind of distribution is underlying it? Now this goes way beyond, of course, thinking that you apply when maybe you're reading some general text. I think it's often not really applied when people are reading scientific text, but you should always ask yourself, whenever such statements are made, your first question must be, what is the underlying distribution? Very often you will not know it, but you should ask that question. And then you should ask yourself whether median and average coincide or not. Here's some practical examples. I just took them out of newspapers or websites when I could find them. So for example, this was on the Guardian. It says they're 17 hours ago, but that is a while ago. And and the headline was saying that the mean apartment price in New York City is $1.4 million. The median household income is $50,000. There's an awful lot of toast in that shortfall, and then you see on the picture some avocados. So a bit of background knowledge is necessary on that. At the time, there was discussion that avocados are expensive, that toast with avocado is very expensive to buy, that young people are able to afford this, and it was pointing kind of to a luxury lifestyle that is not deserved. So in this context, the statement is made. Now, nothing wrong with this statement. No mix up here, because the article does talk about mean and median. That's, by the way, I find very surprising that a newspaper article is using the word median when I guess many people out there will not know what the median actually is. So the Guardian, strictly speaking, does not do anything wrong, but I believe it's still a lie that is being told, because honestly, I don't believe that there's a problem really between apartment prices and household income in New York, because probably, I don't have the facts for this, but probably the apartment prices follow such a power law. So there are few apartments that are very expensive near Central Park, and the further you get to the periphery, the cheaper it gets. And the same applies to household income. There are some jobs, some rich people who earn a lot of money, and the vast majority earns only a little. Now, you can guess who is living where. But that actually means that I would presume that there is no mismatch between the apartment prices and the incomes in general, as far as the distribution is concerned. That it's unfair, and that affordable housing is usually far too little available, is of course unaffected by this. Let's look at this difference between mean and median again, and the relation to the distribution. So in a normal distribution, you have the mean and the median coincide. That's what you can see on the left. And the middle bar is the one that is pointing to both the median and the mean. And a power law distribution is reflected to the right. And in that, the mean is not equal to the median. So this means we should be using this knowledge when judging some values. So strictly speaking, we could always ask about the distribution. So before we make any judgments of our score, we would ask, what is the distribution? Give me the control population, give me the full distribution across all of the control population. Now, Obviously, this would be a lot of data to digest and maybe too much. So can't we have it a little bit easier? And one way to do so is the Z-score. So the Z-score places your score in relation to the scores in the control population. And it uses the two ingredients which are key to the control population, namely the mean value of the control population and the standard deviation. So the Z-score is defined as X, which is your score, minus the mean score divided by the standard deviation. Intuitively, the Z-score is telling you how many standard deviations your score is greater or lower than the mean value of the control population. And that means that no matter what you're measuring, a Z-score of +1 is significant. It means you're one standard deviation above average with your score. Same holds for -1. But as you're getting to 0, that means you're pretty close to the average that you can expect. So the higher the Z-score, the more significant it is. In the middle of the slide, you can see the definition of the standard deviation and the mean value. So for the standard deviation, the square root of 1 divided by n, and then the sum over all values xi from your control population minus the mean value and that term squared. And the mean value is defined as 1 divided by n times the sum of all of the values in your control population. Another score that is frequently reported in sequence comparison is the e-value. It's the expected number of entries with a better score than the given score. So the range of the e-value is between 0 and the database size, and the lower the e-value is, the better. It's calculated from the raw score, the database size, and the sequence size. The formula by which it's calculated is actually pretty complex because it takes a lot of special situations into account. So for example, that the likelihood of matching in the middle of the sequence is a different one than at the very beginning or the end. So let's go back to this question of bias in control populations. So are our biodatabases biased? I first want to give you some general examples of how easily it can happen that bias is introduced. And I have two historic examples for this. One is the 1936 presidential election in the US, where a literary magazine called the Literary Digest made predictions and made a very, very substantial and expensive evaluation to predict the outcome. They apparently really had the goal to have the election before the election. That's how it was propagated. So essentially, the Literary Digest predicted that Roosevelt would lose at 43%, but in fact, he won at 62%. And now, how had they obtained their data? So they apparently mailed 10 million people, and apparently they got the numbers from phone directories, from car owners, and overall they got 2.4 million responses. Now, first of all, if you go back nearly 100 years, it sounds a little bit too big to my taste that they were really able to handle 10 million people. But there is something more problematic about it. How did they select people? Did they really take a representative sample of the whole US population who were able to elect? No, they were driven by what was accessible to them, and that was phone directory and car owners. But go back 100 years, nearly 100 years, 36. Who had a phone who had a phone and who had a car? These were rich people. Now obviously what you vote for will be also governed by your income. Now, there's a dependency there. So there was some very, very clear bias in how they selected data, and the selection was driven by the ease of obtaining the data. And that is, as I explained to you already, very similar to what we do in our biological databases. We work, of course, on the data that is more easy to obtain. Large complexes, large protein structures are very difficult to obtain, hence you find only very few of them in the PDB. Membrane proteins are very, very difficult to crystallize, hence you find only very little membrane protein in PDB. But for example, for disease, many of the drug targets are membrane proteins, so it's very, very important. So that very bias that the Literary Digest created in the 36 campaign, we also have partly in our biological databases. Now, is hence everything in vain and everything problematic and you cannot work with it? No, of course not. You must only be aware of what you're doing and you must judge what you're doing. And it would have been no problem if the Literature Digest had not spoken for the whole of the US population, but if they had made clear for what their prediction held. And I guess for the phone owners and the car owners, the predicted result of the Literary Digest was probably correct. Now, another problem are the non-responders. So the Literary Digest ignored simply those who did not respond, but that is usually also not really a fair treatment. So who would, in that question, not respond? Well, probably also people who are still uncertain, but in election these will be the most interesting ones. Those who have clear what they vote for easily respond. And again, something similar may be the case also in our biological data, that there is some data which is not here, not there, therefore is more difficult to handle. And that is exactly the data that we should pay attention to and not the very, very clear-cut cases that are obvious. So let's look at another means. So we have now the basics of the distributions and the mean and the average and how to judge them with z-score and e-value. Another more refined principle to judge the quality of a search is precision and recall. So imagine we're searching a database and we have given a query sequence, which is an aquaporine, and our task is to retrieve all other aquaporines that are sitting in our database. So in the big circle, you see the database, the left smaller circle are our aquaporines, and the right smaller circle are the retrieved sequences. So both the aquaporines and the retrieved sequences are, of course, coming from our database. They overlap. These are the true positives. These are the retrieved sequences that turn out to be aquaporines. That is exactly what we want. But then there are parts which we're missing. And these are the false negatives. These are aquaporines which we wanted to retrieve with our algorithm but didn't get. And we have false positives. These were sequences we did retrieve, but are actually not aquaporines. And then there are true negatives, that is the big rest of the database, which was not retrieved by our algorithm, and they're not aquaporines, hence with them everything is fine. Now again, when we make judgments about significance, we want to have easy to understand values. And instead of reporting all of these four values, the amount of true positives, false positives, true negatives, false negatives, we derive two measures called precision and recall. Recall is the true positives divided by the true positives plus the false negatives. So these are all of the meaningful hits divided by all meaningful results. The precision are the true positives divided by the true positives plus the false positives. These are all meaningful hits divided by all of the hits. And then the F-score is the geometric mean of precision and recall. So with the F-score, you have one value you can work with. How could you maximize recall? How could you maximize precision? An important aspect is that both precision and recall work kind of against each other. If one goes up, the other one is low. One is low, the other one goes up. So for example, how could you increase recall? Your algorithm could simply predict more and more. So instead of just giving a handful of results, the algorithm could simply return nearly the whole database. Now obviously, if the algorithm returns the whole database, it will also pick up the apophorines. Hence, you could argue I didn't miss anything, but it was not very specific what it gave. So that would be maximizing recall at the cost of extremely poor precision. So how can I be very precise? Well, that's also easy to achieve. I just don't report anything, or only very little. Only those sequences which I'm really absolutely certain that they're aquaporines. Now, if I'm so stringent, it will mean that I'm missing out on a lot of the aquaporines that were in fact in the database, but they were not as easily findable. So I have a very high precision, but I've traded that off by very, very low recall. So that means recall and precision are working against each other. And it's actually very difficult to design algorithms that achieve both a high precision and a high recall. So if you transfer this idea of searching to web search with Google, would you think that Google has high precision or high recall, or does Google have actually both of it? Both high precision and high recall. Now Google is of course amazing. They're the most successful search engine. And that is now very important. I'm pretty sure there is nothing left by chance. You know, that web front end may look super simple, but there is nothing that is just there. Everything is very, very carefully thought through. So the big question is now, can Google do something that is difficult for other algorithms to achieve or not? Because you would think, first of all, that Google does have both high precision and high recall. Why does it have high precision? I query Google for phone number of Michael Schroeder. It will point you to my web page, probably in the first few links, and you could argue it has a very high precision. Typically, the results that you see on the top page are highly relevant. So the precision is good. By the way, as we're speaking of that, one thing I do not know for sure, but here's a hypothesis. Google has this button, I'm feeling lucky. Why is that there? Everything is engineered. Nothing is left to chance on that front end. So this button exists, I'm feeling lucky. I think if something like this exists, it means Google must benefit, and we as a user must also benefit, because otherwise we wouldn't be using it. So how do we as user benefit? Well, we benefit because we get faster to our result. Instead of looking at 10 results and selecting maybe the first, the second, or third, I skip this step, I save about 1 second, and I get directly to the result that I want. There's a certain danger, right? Because if Google doesn't get it right, I'm going to the wrong result. That's why the button is called I'm feeling lucky. Now, what's in it for Google? Google can measure this way how confident I am with Google search result. And Google can measure or can identify those queries where I as a user believe that Google will definitely give me the best results in the first rank. So typically, you know, I used to use this button, for example, for a Wikipedia search. Okay, so that is all good indication. Google has fantastic precision, and they can also measure the precision very, very well because they see where we are clicking. It's of course a little bit of a self-fulfilling prophecy because we can click only on links that Google is suggesting to us. But they have really good and very big substantial data to make those judgments. So does Google have a high recall? So does Google retrieve all relevant web pages? Now this is actually, when you think about it, very, very difficult to answer because how the hell would I know which pages on the whole of the web are relevant to my query? Now Google is telling you, I found about 1.5 million documents. Isn't that a little bit strange? All these big computers, and it's not possible to give me the exact number. It's telling me pretty precisely how fast it was. It took 0.3 milliseconds. So the answer is, well, that is very difficult to judge because you cannot access all of these 1.5 million results. If you click through the pages after some pages, it's over. You will not get any further. For Google, I haven't done so, but for Yahoo, I did. And I think at some point, a few years ago, it stopped at about page 100. So you could not go any further than page 100. So that is really, really little of those millions of search results that are relevant. And I can tell you, as you're flicking through the pages, the results get really, really poor. So that is pretty amazing. Google really, and then that holds for any other search engine, spends really a lot of effort to make you believe that the precision and the recall are both high. That the precision is high, you can test because you can click on all of the top results and check whether they're good or not. About the recall, you cannot test because you do not have access to the full list of search results. But Google appears to achieve both high precision and high recall. But of course, at the end of the day, everybody's cooking with water, and that means also for Google it's difficult to achieve both high precision and high recall. And if Google was forced, for example, to lay open all of the search results, and maybe it would then decide to limit the search at 50 or 100 search results, then of course, right away, the recall would be lower, the precision would possibly still be high, but you would see that Google would be in exactly the same conundrum as everybody else is, trying to optimize and balance precision and recall. Another very important aspect when judging the significance of results is robustness, and a technique called bootstrapping. I'll just sketch it here in one slide. We come back to bootstrapping when we look at multiple sequence alignments and phylogenetic trees in a few weeks' time. But for now, I want to explain to you the principle because it belongs here into the judgment of significance. So for any of these techniques, you want robustness. And robustness means that a small change in your data should only lead to a small change in the results. Now, if, for example, your protein that you used as a query would be truncated, 2-3 residues are missing in the front or missing in the back, or there was a sequencing error, and you actually have the wrong residue at position 53. None of this should lead to significantly different results. If it does, then you have a problem, because you cannot be certain that data is fully accurate. Neither your query may be accurate, nor the data that is in the database. It is not provably correct. And you can see that beautifully in the databases. Entries get frequently updated. After a while, it turns out there was a sequencing error and some positions are different than was thought. So that means data is always error prone. And that is why robustness is so important, and you should measure it. And there's of course an easy way this bootstrapping can be generally applied everywhere because simply drop some of the data, rerun your analysis, see what you get out, and compare it. And when you drop a bit of data, do it over and over again in random parts, you should still come to the same conclusion. And then you know it's robust. It's robust against the error that you typically expect in your data. So, to complete today's lecture, let's look at some general pitfalls in data. And again, I'll give you a high-level example, but it applies equally well to all of the biological data that we're dealing with. So it's a pretty funny example that I came across with. And that was a statement that there are about 150 coconut deaths per year. Now, it's really funny and it's interesting because you would say, yeah, of course, coconut can fall down from palm trees, somebody's walking below it, gets it on the head, and is dead. This is happening. It's pretty unlikely, but then, we have long beaches, it can happen, 150 people per year around the whole globe. That could be the case. In fact, it's really interesting from where these numbers come from. Because you can go into scientific literature and there's in fact a paper that is about coconut death. But the first question is, first of all, where does this number come from, 150? Why is it 150? Is there an agency that is reporting the coconut deaths? And would, for example, Germany have such an agency? Hardly any palm trees. Why would the government pay for such an agency? But even with very little palm tree, there could still be a chance that somebody in Germany is dying of a coconut falling down from a palm tree. Maybe somewhere in a botanic garden. So obviously there are no registries. But you have many examples where registries exist and an official counting is done. So think, for example, of the corona crisis, where the death and the number of infected people are counted. And all of the states have health systems that organize this counting, and they should also make sure that the way the counting is done is the same across the whole country. But as you can imagine, things may vary already between countries, because maybe they're counting slightly differently. And when you think especially of the corona crisis, you know that, for example, in Germany, the Robert Koch Institute was counting differently than a university in the US that also took some news articles into account and therefore had a slightly higher number available. So simply counting is very, very difficult. It requires an organization, a national organization. It requires standards how the counting is being done, and they must be, in the case of these coconut deaths or kind of in a virus outbreak, they must be internationally accepted. Now, most likely, no registry in a country would count the coconut death, so probably this number was generated differently. It was probably estimated. So if it's estimated, then how was it estimated? What was the procedures? What were the standards that were applied? And that you don't know. So most likely, how was that done? So there was one case, as pointed out in this paper, and then maybe it was calculated from there. And the judgment was, okay, there was one coconut death in this country that has a coastline of X kilometers. Then if I translate that to the sum of coastlines across the entire world, I get number Y. Maybe somehow like that. Maybe not. But we should know. Here's another example that I like. The headline in a German newspaper was Berlin is the single capital, and it was showing the picture that you see here. This is very, very misleading. The photo is showing a woman, looks a little bit like a couch potato, hanging there on the sofa watching TV. You see she moved into a new flat. So that doesn't look, or that is clearly pointing into one direction. So young woman, single. But how was this data actually obtained? Did they take a representative sample of the population and ask them whether they're single or not, and then draw up the numbers? No, when you think about it, for a newspaper, this would be far too expensive. So what could be actually an easy way to get these numbers? Right? And there we again at the question, is it easy or difficult to obtain data? People often go for easy data. So how could I find out something about singles without doing a lot of work and asking many, many people? Well, I can look at the major cities, and I can simply call at the Bürgeramt, at the registries, um, and I can get anonymized information about the flat occupancy. So I can ask, for example, how many single households exist in Berlin, in Munich, in Hamburg, and in Dresden. This number is publicly available. But a single household and a single is probably something very different. A single household may be an old person, happily married for 50 years, and the partner died, and there is a single left. Or there's actually a couple that simply has two flats, and they don't share a common flat. These live in single households, but they are not single. Or especially when you take Berlin, the former capital before Berlin was Bonn, and you still have today many civil servants who are just working in Berlin, but their families are in Bonn. So they're frequently shuttling between the two cities. And probably many of them maintain a small flat in Berlin. So essentially this means very misleading data. And that is also a common mistake that is frequently done in papers and also in our biological databases, and that is that you're using aggregates. So what have we aggregated? We have kind of put apple and pears here together with the single households. We have put old people together, young people who are sharing flats, young people who are really singles, civil servants, and so on. All of this was aggregated into one number of the single households. If we would break it down, the numbers would look different. There would not be such a clear trend, and it will be not so easy to make a nice headline for a newspaper out of it. But it's, of course, what at the end of the day would be really true, and that might not be as shiny as you like it to be. Another example about why it's so difficult to get big data. The Lanarkshire milk experiment ran in the 40s, I think, and 10,000 kids were checked for several months on whether milk was beneficial for them or not. And essentially, the whole experiment, although big, costly, long duration, did not produce any significant results. And the reason was, for example, that mistakes were made in the capture of the data. The experiment ran from February to summer, and the kids were weighed with clothes on. Now, obviously, in winter, you will have a heavy jumper and some heavy trousers. In summer, only a t-shirt and shorts. That makes quite a substantial difference on the balance. The teachers were allowed to choose the kids who received milk and who didn't. Now, obviously, the teachers will be biased. Maybe the skinny kid, they gave milk, whereas the little bit bigger kid, they said, oh yeah, fine, you can do without milk. So such an experiment must be blind, and you must really randomly choose and assign and not have this selected by a person. So creating unbiased data and measuring in an unbiased way is very difficult to do. Finally, another example. This is from Spiegel, major German newspaper, and it was saying these are the top earners among the physicians. And it was breaking this down into radiology, eyes, urology, and so on. And radiology was basically the biggest salary. And when you're looking at this, you say, wow, 850,000 per year. That is much, much, much more, certainly much more than any of you student probably has available per year. But then very misleading because an aggregate was built here. The headline is talking about the physicians, but the numbers are not really physicians, but these are groups of physicians. Praxen, as it's saying. And as radiologists use very expensive machinery, typically there's more than one radiologist working together in one praxis. And that is simply also the reason why obviously that group of physicians is generating more income than if a physician is just working on their own. So here again, an aggregation was carried out that was misleading. So, take-home message, understand what a control population is, understand what the structure of that control population is, what the distribution is, what the mean, median, and standard deviation are, judge your scores in relation to these control population with that score e-value, understand precision and recall when you're searching over a database, and generally understand the pitfalls of the data that you're working with that is sitting in the databases, and generally the problems that you can actually create as you're analyzing this data. Thank you very much.